everyone, this part will focus on the capacity and range of buffer solution. When a small amount of strong acid or strong base is added to the buffer solution, the pH of solution basically remains unchanged. If the added concentration of strong acid or base is close to the concentration of the conjugate base or acid of the buffer system, the buffer solution is extensively diluted and shows little buffer effect. The buffering capacity of the buffer solution is limited. Mathematical expression of buffer capacity. Beta, the buffer capacity, the physical meaning of which is that the amount dB of strong base making the pH of 1 liter solution increase d pH unit, or the amount dA of strong acid making the pH of 1 liter solution decreases d pH unit. Since the increase of acidity makes the solution pH decrease, a negative sign is put in front of dA divided by dpH to make beta positive in all cases. The greater beta is, the stronger buffer capacity the solution has. 2. Relationship between buffer capacity and solution components. Taking HAA as example. Assuming the total concentration of buffer is C, the formula of buffer capacity can be obtained by transformation. If the distribution fractions of HA and A are expressed by concentration, a calculation formula of beta related to the concentration ratio of two forms can be obtained. In this formula, HA and A are the equilibrium concentration of conjugate acid and base, respectively. So there are two factors impact on beta, C, and the total concentration of conjugate acid and base, and the concentration ratio of conjugate base to acid, which is called buffer ratio. Next, we will talk about how these two factors influence on buffer capacity in detail. First, when C stays constant, the relationship between buffer capacity and buffer ratio is discussed. For buffer solution of HAA, the simplest calculation formula of pH is pH equals pKa plus log buffer ratio. So the relationship between beta and buffer ratio can be deduced indirectly by the relationship between beta and pH. Plot the curve with pH as abscissor and beta as ordinate. It shows that the buffer capacity changes regularly with the change of pH. That is, the buffer capacity also changes regularly with the change of buffer ratio. Then, how is the change exactly? Let's take a close look. According to the calculation formula of pH, when the buffer ratio is less than 1 and pH less than pKa in the red curve region from A to O, beta increases with the increase of pH. In the green curve region from O to B, the buffer ratio is larger than 1 and pH larger than pKa. Thus, beta decreases with the increase of pH. At the middle O point, the buffer ratio is 1 and pH equals pKa. It can also be seen from the figure that the more the buffer ratio is close to 1, the bigger beta is, and beta reaches climax when buffer ratio is 1, that is, pH equals pKa. Similarly, the far the buffer ratio is from 1, the smaller beta is, and even lose the buffer capability. When the buffer ratio is between 0.1 and 10, the buffer solution possesses a buffer effect, which means the pH buffer range of buffer solution is pKa plus or minus 1. Generally, the buffer capacity of conjugated buffer solution have characteristics as follows. First, beta is proportional to C, that is, beta increases as the increase of C. Second, when hydrogen equals Ka, beta reaches max, that is, beta max equals 0.575 C. Third, buffer range, pKa minus 1 less than pH less than pKa plus 1. That's all. Thank you.